Good morning. So, bright and early we start with our aberrations again. So in yesterday's lab exercise, you were asked to optimize some systems for certain aberrations. So since we had looked at spherical aberration in coma, that's what you did in the lab exercise yesterday. And you might not have finished the exercise yet, but you've also been asked to change the shape of a lens. So that means keep its focal length constant and then see how the aberrations vary or depend upon the shape. And once you do that, you need to plot a graph of this kind. Although the x-axis is plotted against, so what you're varying along the x-axis is the shape. There are very specific instructions on what you actually plot along the x-axis. So please go through the document carefully, otherwise you will not get this form of the curves. Okay. Has anyone finished the exercise? One of the reasons of plotting curves like this is you are able to see where you can minimize more than one aberration, or in this case you're saying for a particular focal length, you're not changing that, you find that there's one shape that gives you a minimum of spherical aberration in coma, and clearly that would be a good shape to use in that case, right? So we've only plotted the two aberrations here, but of course you can plot the other aberrations. You can look at astigmatism and distortion and color and see how they are affected by this parameter. Okay, so I encourage you to do that since it gives you an idea of what affects a certain aberration or not. Okay, so we move on to the next monochromatic aberration, which is astigmatism. Okay, what is astigmatism? I can see several of you wear glasses, so I'm sure you would have heard the term astigmatism before, right? Okay, so you've got the idea that, well, this is what every aberration is doing, right? Different annular zones are doing something, different apertures are doing something. So where does astigmatism arise? First of all, astigmatism arises when there's asymmetry. Okay, so it is an aberration that arises only when there is asymmetry. So if I have an on-axis point and a circular lens, circularly symmetric lens, then you will have no astigmatism. You can see in this particular figure, the astigmatism is arising because you're looking at an off-axis point, and that's where the asymmetry, the lens is circularly symmetric, but you have a off-axis point, and that is where the asymmetry is arising. Now, I hope I have this figure. This is just a zoomed in version of what's happening over here. So if you look at this, there are the planes have been, two different colors are used to designate the planes, okay? So the sagittal plane is in blue, and that is the rays that lie in the horizontal plane, and the meridional plane is in gray, and that is the perpendicular plane. So you can imagine you have a fan of rays that lie in the meridional plane and a fan of rays that lie in the sagittal plane, and they come from this off-axis point and hit the lens. Now you already know that the meridional rays, if this is your lens, this is the optical axis, the meridional rays are coming from this off-axis point, and you can see they all hit the lens in a very different manner. There's no symmetry in the way they hit the lens. So this is for the meridional plane. On the other hand, the sagittal rays are all, I can't really draw it, but let's say this is my sagittal. They're all hitting this. So when I look at it from the top, they're going to look symmetric. This is the top view for the sagittal, right? So there is symmetry still with the sagittal rays, and there isn't any symmetry with the meridional, and there's a difference between these two, okay, for an off-axis point. So it may not be obvious in this figure. If I look at these two, if it seems here that both the sagittal and the meridional rays are coming to focus here, but if you look at this, you zoom in and you look closer, this is what is really happening, right? And what is happening here is the set of fan of rays that lie in the sagittal plane, they are coming to focus over here at this point. So the blue are the sagittal, and unfortunately the color has changed. So in this zoomed version, the red plane is the meridional. Okay, what was gray over here. They are coming, so this is like a sagittal focus, but the red rays are focusing somewhere over here, right? So the rays that are coming from the meridional plane, they come to focus at one point. After focus, they go on diverging. The sagittal rays come to focus at another point. After focus, they go on diverging. Now, ideally, these 2 points should be the same point. And if this was an on-axis point, this would be happening, the focus would be happening at the same point. But because of the asymmetry, this is not happening at the same point. So what does that mean? At this plane, where the tangential rays come to focus, the sagittal rays have not yet come to focus. So if I were to look at that image at that point, of course the image is formed by all the rays that are there, not just by the rays that happen to be in focus there. So if I were to look at the image at that point, what do you think that image would look like? I have a point object, my ideal image is a point image. And when I look at the tangential rays, they've all come and focused to a point. So the tangential rays are forming a point at that place, at that location. The sagittal rays are coming like this and they form a point later on. So at that plane where the tangential rays are focused, what do the sagittal rays look like? So I have my tangential rays coming to focus at this point, and my sagittal rays are focusing at this point. So what does the sagittal look like here? What is the focus of the sagittal rays? It's a line, right? So I have this, the fan of rays in this plane, they are coming to focus. Just think of, if I'm looking from a top view, I have a fan of rays coming to focus here. If I look at them at any other plane, it's a line. At this plane, and I can't draw it because it's a top view now, so the tangential rays are just going to look like this. But there's a whole fan of rays there. They are coming to focus at this point. At this point, what will the tangential rays look like? Another line. But will the lines be exactly the same? So maybe this image helps you a little bit. In this case, my focus, so I'm now looking at the tangential focus. This is the line which is basically caused by all the sagittal rays, right? So the tangential rays have come to a point focus, but the sagittal rays are spread out and I get a line like this. What will I see if I look at this surface? It's still a line, but it's a vertical line. Okay. So remember now, even in spherical aberration, we said the focus happens for the paraxial rays at some point, the focus happens for the marginal rays at another point, and I can consider that there is a focus that has happened everywhere between these 2 points. So it was as if the focus was spread along the optical axis, right? And we then decided that the paraxial focus, although we keep saying that's the ideal focus, it actually doesn't give us the best focus point, because the tangential or the marginal rays are so far spread there that your spot is overall very large at the paraxial plane. And then we moved along the optical axis till we found the plane or the circle of least confusion, and we said that's the best focus if your system has spherical aberration. Again, in astigmatism, you find that the focus varies along the optical axis, but it's not varying in terms of a circle of different diameters. Here, it's varying in terms of an ellipse. So, the tangential focus, I call this the tangential focus, but this line is caused by the spread of the sagittal rays here. I call this the sagittal focus. That means if all the sagittal rays have come to focus, but the tangential rays were focused much earlier. They've continued to diverge, and so their rays are spread out like this. So I have a vertical line here, right? And somewhere in between, I'll have the circle of least confusion. Okay. Now this arises because the object point was off axis. The moment I move to an on axis point, I cannot tell the difference between the meridional and sagittal rays. You should be able to see that. I can always rotate my object, and what I'm calling meridional and sagittal, I can interchange that, right? So for an on axis point, if my lens is symmetric, there is no question of having astigmatism, right? So astigmatism, each aberration you can see affects the system very differently. Spherical aberration, yes, it was an aberration that affected focus along the axis, but it was symmetric. You could identify a nice center of gravity to your image. You could find a plane where the spot is minimum, and that was not the paraxial plane. Coma, you had no longitudinal error, you have only a transverse error, but the center of gravity is not easy to locate. You have to use some other means, and you get this strange comet-like shape, makes your image really bad quality. And now we're saying in astigmatism, again, you have a longitudinal variation, but it's not symmetric about the optical axis. You have this ellipse, and this ellipse is rotating as you move along the optical axis. So at the tangential focus, this is what you'll have, and I've drawn the RIC curves for the meridional or the tangential plane as well as the sagittal plane. Now you can see we call this the tangential focus. So if I look at the RIC curve for the tangential rays, there's zero error because they are all at focus. Yes, the rays are all, so they are all coming to the focus point. So all these different tan U's, but the error at this point is zero, and that's what is indicated in this curve, right? On the other hand, if I look at the sagittal rays, right, at this plane, they are spread out like this. So I have this spread over here, right? And that's why you see a variation in the sagittal. If I move a little further down the axis, I have the best focus. So it's neither this is the best focus, it's like a compromise. Neither are the sagittal rays focused here, nor are the tangential rays focused here, but this is where I get the minimum spot or the most circular spot, right? And both RIC curves of sagittal and meridional show variation. On the other hand, if I move further down, now I've come to the plane where all the sagittal rays have come to focus. So each ray coming to focus has a different angle, but at that point of focus, they are all at the same place. So the error is 0, which is why the sagittal here shows 0 error for all rays, irrespective of their angle. The meridional rays, on the other hand, have now spread out in this direction, and so this is why the meridional rays, the RIC curve is non-zero. And as you move for increasing angle, you see the height is increasing, so you have a linear variation in the error here. Okay? Is that clear? Take some time and picture it. Once you picture it, it's pretty straightforward. Once you see this fan of rays, which is why it's so important to get your definitions and understanding of the meridional and the sagittal rays. Now you see, if you understand what those rays are, this aberration becomes easy to picture, because you know we're talking about the fan of rays in a particular plane, right? Now, up till this point, we've always assumed or imagined or talked about aberrations as if aberrations are a bad thing. But we can use aberrations, or not all aberrations, but we can use astigmatism to help us do something. And in fact, I said, if you have an on-axis point and a circularly symmetric lens, you will not have astigmatism. And that's clear because your sagittal and meridional for on-axis don't have a difference. So sometimes in an optical system, people will actually use what's called a cylindrical lens. Now, a cylindrical lens breaks the circular symmetry. So if I were to attempt to draw a cylindrical lens, this would be one face of the cylindrical lens, and the other face would be curved. Okay, it would be like if you took a cylinder and then you cut it in half at the diameter, and then you use that surface as a lens. Now, how is this different from the lenses we've been looking at all this while? Well, the lenses that we've looked at, the spherical lenses, they had curvature in this direction and they had curvature in this direction, right? What did that mean? When you had a beam of light, so let me draw a side view, that's just a side view of our spherical lens. So remember, in this view, you only see the curvature in this direction. But if I were to look at the top, so this is a side view, if I were to look at the top view, it would look the same, right? Now, if I have light incident on this lens, it comes to focus because it's bent by this curvature. In this, the same beam would come to focus because it's bent by the other curvature. There's this curvature and this curvature. So these rays are getting bent, the sagittal rays are getting bent, the tangential or meridional rays are getting bent. But in a cylindrical lens, there's curvature only in one axis. There's no curvature in this axis. So the bending happens only in one. So every ray that bends here, it bends here, it bends here, but there's no sideward bending. What's the focus I will get? You will get a line focus, right? And you must have seen optical systems where you have a line of light, right? So sometimes you don't want a point. If it's an imaging system, you want every point on the object to be a point on the image. But you're not using optical systems only as imaging systems. Sometimes you use them to scan, or you use them for a variety of reasons. Maybe you need to heat up a certain region, so you have a powerful beam of light. Sometimes you need a line of light rather than a point of light, and a cylindrical lens does that. Now, I can further use that in some systems where I want to have astigmatism. Now, why would I want to have astigmatism? The clue to that is thinking about what happens as you move along the optical axis in a system with astigmatism. So, you tell me that, what happens? We've just gone through that, but I'll ask you again. what happens when you move along the optical axis in a system with astigmatism? What are you going to observe as you move along? So the focus, but the focus is a line, it's right, or strictly speaking, if you consider all the rays, it's not really a line, but it's like an ellipse. But the ellipse rotates as you move along the focus. So the major axis of the ellipse lies in one plane, and as you move, that is rotating, and finally the ellipse, major axis of the ellipse, is in a orthogonal direction. And in between, somewhere that ellipse has changed to a circle, and then again it becomes an ellipse, and right? Okay. Can I not use this? If the focus is changing as I move along the optical axis, can I not use this? Say I wanted to find out in a particular system where the focus was, right? And many systems actually do this. So they may use some inherent astigmatism that is present in the system, but if they don't have inherent astigmatism present, they will actually introduce a cylindrical lens. So you're introducing astigmatism. Now please note, I said on-axis points do not suffer astigmatism, but that's not true if I introduce a cylindrical lens. Because I also added the rider, on-axis points do not experience astigmatism if the lens is circularly symmetric. And the moment you introduce a cylindrical lens, you're breaking the symmetry. So even on-axis points will have astigmatism, right? Because the behavior of the sagittal rays is going to be completely different from the meridional rays, even for an on-axis point, right? What happens in a CD system is so one of the common places where this is used is in a focusing of a CD system. Okay. So astigmatism can be used to help find the focus. So the CD, and we'll look at that in more detail, but basically the CD system and other similar systems has a lens which has the ability to move up and down, okay? So you can control that movement. Now, as it's moving, you're changing where the focus, maybe the focus happens here, then you move it down, then the focus will happen here. If you move it further down, the focus, right? So you're changing, by moving the lens, you're changing where the focus happens. Okay. I want to adjust the height of the lens with respect to this surface such that the focused point lies on the surface. Now, how do I do that automatically? If I have a detector which has 4 quadrants, so it's called a quadrant photodetector. Now let's imagine, so let's say we'll call these A, B, C, D, right? I have to orient my system, or I have to orient the detector such that the tangential focus initially is like this. So as I move the lens, the detector is here and it sees this. If I move the lens further, let me just keep these ready. If I move the lens further, I'm going to go through this region, and if I move it further, I'm going to go through this region. Now, the electronics, the quadrant photodetector basically means you're able to acquire the image from each of these quadrants independently. And so people either do an operation of AD minus BC or A plus D minus B plus C. And you can see that if you have aligned your system correctly, when you're at this position, you will get a 0 over here. So when that signal is 0, you know you're at the best focus. So you can use that for automatic focusing. Okay, and this is exactly what is used in a CD pickup or DVD pickup and in many other optical systems as well. So you are actually using an aberration to achieve something useful. You can also think of astigmatism as, so what the explanation we looked at right now is, this is what is happening, this is why it's happening. Sagittal and meridional rays behave differently. We use these two fans of rays, or the fans of rays that lie in these two planes, to make it very clear why there is a difference in focus. But clearly this effect is being felt through all the rays in every plane. So we have taken only this plane and this plane, but you have a whole host of planes of rays, right? And you can think of it in another way as, at one focal plane, if this was the object, so you had like a bicycle wheel with spokes, astigmatism causes one set of features to be in focus at one plane and another set of features to be in focus at another plane. So if I was trying to image such an object, astigmatism is going to prove a bad thing, because clearly where I get best focus for some features, I'm getting the worst focus for the others. And I would have to find some plane in between where I say I don't get best for either, I get something that's acceptable for both, or the different sets of features. Okay, but in the previous example of searching for focus using this, then I'm taking advantage of the aberration, or I'm actually introducing the aberration so that I can use it to find the best focus point. Okay, now the final aberration we look at is field curvature. So again, if we go to an off-axis point, it should not be surprising that the ideal image surface is not actually a planar surface but a curved surface, right? We have always been talking about, if you have an optical system, if you have an object, then, and I look at, let's say I have an object which has some height, we have always been drawing the image like this. That means we are saying, what happens on this plane? But the spherical surface isn't the surface that gives us the best image. So it shouldn't be surprising that the best image plane is actually a plane with curvature, which itself is part of a sphere. Now we are compromising and using a planar image. Why don't I use a curved surface if the curved surface is the best surface? If my image is being formed on a curved surface, why am I capturing it on a planar surface? I'll remind you of something else, maybe that will help you answer that. Why did we go to spherical? If spherical is not the best surface, why are we using spherical? It's easier to manufacture. Imagine if every screen, we're saying the image capturing screen should be curved. Now imagine every single phone of ours has a screen. Right? Every camera has a screen. Every imaging system has a screen. It's so much easier to manufacture flat screens. And if I start saying manufacture curved screen, well, the curvature has to depend on the optical system. Here, whether you're buying a smartphone of a certain size or a slightly larger smartphone, everything is flat. I don't have to worry about what is the optics that I'm going to use, what is the size of the camera, what is the curvature therefore that I need. I may make my sensor slightly larger or smaller, yes, but it's always flat. So I don't have to worry about the curvature of the system. If I change the size of my optics, well, maybe my screen has to be this big, or maybe my screen has to be like this. I would have to custom make it, and anytime you have to custom make something, the cost shoots up. Plus, it's just so much easier to fabricate flat screens, right? So again, we are living with the fact that the best image is being formed on this surface, but we are going to capture it on this surface. That means there's defocus everywhere here. Now, if this defocus is within the depth of focus, it's acceptable. So I have to design my system such that this error, and this is called the Petzval curvature. This. Now, if you have an on-axis point, the tangential rays, the sagittal rays, and this Petzval curvature, these three surfaces all lie on the same surface. They're all the same surface. But the moment you go to an off-axis point, these three surfaces separate. Okay, so I have, like, you could consider the Petzval curvature as like the paraxial curvature, the best curvature you get even for on-axis. Then the tangential rays will focus on one curved surface, which is different from where the sagittal rays focus. And you can see this two images over here. The first image is when you're at the plane closer to the paraxial image point, and you can see you're imaging something like this across, and closer to this, you're at this plane where these rays are in focus, right? And if you move away here, these rays are in focus. And if you move away, then you find these rays are in focus. So you can imagine if your surface was like this and you say the paraxial rays are in focus here and the outer rays are in focus here. If I move my screen, when they're here, I will see these rays in focus. And when the screen is moved here, I'll see these rays in focus. And that's what you're seeing in these two images over here. So my image is formed on a curved surface. The paraxial rays are focused closer to the axis. So when the screen is here, you get those rays in focus. And then I move the screen and the outer ones become in, these regions are in focus, and this is all blurred. Right? Okay. Yeah. So this is what I was saying, for an off-axis point, these three planes start to separate out with the tangential rays. For a convex lens, the tangential meridional rays, they come closer to the lens, and they're roughly 3 times away from the paraxial plane as the sagittal rays are. So you can see I first have all the tangential rays focused here, I have all the sagittal rays focused, and this is the Petzval curvature plane. If it's an on-axis point, these three will all merge and become one curved surface. Okay. Again, if I look at the longitudinal error, this graph is now showing the longitudinal error. If I can somehow add a lens or set of lenses to the system that pulls this away, right? This is actually a nice figure. This shows the longitudinal error. And you can see this is for a corrected field. Okay, so if I was looking at the longitudinal error of an uncorrected field, plot would be exactly this, right? This is the height of the ray, and this is the longitudinal error. How much does it deviate from the paraxial plane, right? So the tangential has the largest error, the sagittal has smaller error, right? If I go to a lower height, let's say I'm at this height, the error is less, but always the tangential has more error. So this graph itself gives you the longitudinal error. And again, you can just look at this and get an idea of correction. With this kind of lens, this is the kind of error you get. So if you could replace or change the optical system so that the tangential rays now did this, then I get what's called an artificially flattened field. Okay, and you can see this single lens here has caused this kind of astigmatism. And the diagram below, which has 4 lenses in it, is used to flatten. So you are adding convex, concave, you have something that's slightly concave over here. So these set of 4 lenses are required to flatten the field and get something where your best image will form here. Okay. Now you can buy adapters or objectives for a microscope, and the amount of money you pay for that objective depends on how much aberration correction has been done. And some of the most expensive objectives are the ones that give you flat field over large area. And of course, it depends on your application. If it's a simple lab demo or school exercise, you're not going to worry about flattening the whole field. But people who are using it for medical diagnostics or studying biological phenomena, you will pay lakhs of rupees for an objective because it's been designed with the optics that will actually flatten the field. That means on your flat screen, you get everything in focus. Okay? Okay, any questions? When I ask questions, there are no answers. When I ask for questions, there are no questions. Okay, so these aberrations, as I said, so up to astigmatism, they actually, there is clear defocus, right? Field curvature, yes, if you're at the paraxial plane, there's going to be defocus, but there is actually a surface. What field curvature is saying, field curvature is basically giving you the deviation from the paraxial plane. And when you talk about field curvature, there is a surface where there is perfect focus. Right? In spherical aberration and in coma and in astigmatism, there is no surface where there is perfect focus. You are finding a surface where there is, or a plane or a point where there is minimum aberration. It's not that there is perfect focus. But in field curvature, if you use the paraxial plane, the so-called paraxial plane, yes, you will see defocus, but if you developed a curved screen or a curved sensor, you would be able to get perfect focus, right? You're not compromising. There is perfect focus. So that's why right at the beginning, I had differentiated these 3, spherical, coma, astigmatism. They actually affect, they deteriorate the image, whereas in field curvature and distortion, there is perfect focus. Although often in field curvature, it means because I'm using a planar surface, I am losing out on that perfect focus. Okay. However, because there's perfect focus, I can actually do something to my system and change that curved surface to a flat surface and get my perfect focus. Distortion is where I have perfect focus, nothing looks blurred, but you can see this top image here is what should have been the image. So I'm imaging a set of grid lines, and I should have, and they're perfectly perpendicular square areas between these grid lines. And this is what I should get as an image. And because of the distortion of the system, I get any one of these other 3 images. Nothing is blurred, nothing is hazy, nothing is out of focus. But the points are no longer perpendicular. I don't have nice square areas. So it's almost like this image was stretched. It's in focus, but it's been stretched or it's been pushed, right? And so this is called barrel distortion. It's pretty obvious why. It looks like a big wine barrel. This is pincushion distortion, because if you consider a pincushion, when you stick the pins into it, the way it deforms. And well, sometimes optics people be a little bit adventurous, so they call this mustache distortion. I leave it to you to figure out why. Okay. And so an idea of what this is, an image taken, it does not have distortion, but with certain lenses, in this case, we've just digitally adjusted the image to show you what it would look like with distortion. But it's sometimes in an optical system, you will actually see the lens will itself give you distortion. I mean, certain software have digital tools to give you vignetting, for example, or this, because people may use it to enhance something in a photograph. But often your optical system itself will give you that effect, right? And it may not be a desired effect, and we'll see where that arises. Okay, so you can see that this image is kind of, everything is there, but it's slightly stretched or out of proportion, if you will. How do you quantify distortion? Well, let us say from this is the optical axis, a point should have lain at some position. This is the ideal paraxial point, the image, but instead of lying here, it lies a distance d away. So the distance from the optical axis, the ideal distance from the optical axis, if you said that was h and the extra distance is d, then we call distortion just the ratio d by h, and it's a percentage, so it's d by h into 100. Okay, and if d moves further out, it will be positive. If it moved closer, it would be negative, and that tells you whether you're stretching or compressing your image. Okay, so now when you go and look at your aberration curves, you will now see the distortion curve, and many systems may have very low levels of distortion, so up to a percentage or so is fine, right? But you really don't want in a typical system to have high values of distortion at all. Okay. So we've looked now at a number of different aberrations, and maybe in yesterday's lab class you also started looking at what affects those aberrations. Okay, so I want to ask you a question now. Let's say I had a lens and I'm looking at an on-axis set of rays. So it's coming to focus here. Now I take a stop and I move the stop. So I have a stop, okay, and I now move the stop. What do you think happens to the spherical aberration in the system? Nothing happens. Spherical aberration is independent of the position of the stop. It is not independent of what other parameter of the stop? The size. Because if you change the size, you're then saying these rays are not going through, and we know spherical aberration is variation in focus with aperture height. So if you change the aperture height, you are affecting the aberration. But for an on-axis, spherical aberration is on-axis, that's unaffected by the location. So if I keep the size of the stop the same and I move it up and down, it does not affect spherical aberration. On the other hand, let's say I took the same system and I had a set of off-axis rays coming. Do you think it would be affected by the location of the stop? Yes, it will be affected by the location of the stop. In this example itself, you can see that if I had the aperture here, the ray that goes through is this. This is what goes through. But let's say I took the same system and I put the stop here. Which set of rays are going through? This goes through here, but then finally what's passing through is this part of the system, right? It's this part of the ray that is going through. So which part goes through which part of the lens is determined now by the location of the stop when it's an off-axis beam coming in, right? So now to understand how I optimize and remove aberrations from my system, I must know what they depend upon. And to do that, I must understand the aberration. So I hope by looking at these 5 aberrations, you have a slightly better understanding. The lab exercises are aimed at helping you get that link between the different tools you have. What are the tools you have? You have the shape of the lens, you have the location of the stop, you have the size of the stop. These are some of the immediate tools that you have. And some of the exercises are going to give you, or the exercises will give you some of these links. I want you to play around with it so that you understand all of these links, because that is how you're going to be able to correct the aberrations. And you shouldn't get surprised. You say, I've put a variable, I've put an operand, I'm optimizing, and my aberration is not decreasing. Well, spherical aberration is not going to decrease if the variable you put was position of stop, right? However, if you put shape, kept the focal length constant and changed the shape, then you'll affect the spherical aberration and you'll affect coma. So the next class and what you should finish for yesterday's exercise are all now to do with how do I get rid of aberrations by choosing the appropriate parameters to adjust. Okay? And then we'll also in the next class look at chromatic aberration.